Okay, so welcome to my presentation. I'm Jim Mainprice. I'm the interim professor for machine learning and robotics at the University of Stuttgart. And I'm going to talk about human behavior models derived from data for proactive robots. So humans have really this feature that they can share space in a collaborative way. And as we see in the scene in this restaurant, this kitchen restaurant, it's that they are able to coordinate themselves using a model of what the others are going to do or have to do. This is because there's a task being performed, but there are also some obvious clues that are independent of this task. So, for example, humans don't collide with each other and coordinate themselves in the workspace in this way. So in robotics research, designing control architectures for robots, we usually have a divide between the state estimation and the optimal control algorithm, where the state estimation is building a state representation, which is usually a vector. And this vector is usually imposed a certain structure by the roboticist who designed the architecture. The control algorithm are usually a collection of motion planning algorithm, control algorithms, and so on. And they produce an action at every time step. So the big challenge in robotics is usually to handle the uncertainty that comes from the state estimation in order to produce actions which make sense, but make sense given that uncertainty. This uncertainty usually comes from the limited sensor capacity. So, for example, cameras and LiDAR type of sensors perceive only a portion of the workspace or the state space if it's joint encoders, and this generates this uncertainty. So, as I was at the Max Planck Institute, we developed a state-of-the-art robot perception and control architecture that is able to react to changes in the environment. Especially I worked on the world model, where we had a dense world model which reasoned on a occupancy grid, which was processing point cloud data coming from the Kinect sensor here. And in order to react to changes in the environment in a very fast way, we further sparsified this representation by considering only the closest point between the robot and the environment. So this mechanism was interlocking multiple control loops in order to produce this behavior that we see here, where we have the robot computes a global movement that goes around the object, but as the workspace changes, as I put the bottle here in the way of the robot is able to react very quickly at about 100 Hertz. Another component aside to the world model that is very important for considering dynamic environments where humans might change the environment is the motion planning algorithm. So here we used trajectory optimization, where constraints about the environment and the smoothness of the motion itself or the path are combined together, and we then solve the optimization problem using some kind of gradient descent algorithm. Here actually a Gauss-Newton method allows us to compute the update, and this happens really fast with the inner loop. So this also allows us to consider dynamic environment because we can warm style the optimization at every time step in a model predictive fashion by taking the previous solution that was considered as an initialization for the next one. So here we see the system in action from the point of view of the robot, and we see the octomap occupancy grid being updated at 40 Hertz, and we compute the sign distance field at about 10 Hertz, and the closest points are also being computed. So it's important to note that we used tricubic splines in order to smooth the data and compute gradients for the trajectory optimization and the control pipeline. So this is nice when we have humans moving in the workspace and we can consider them and avoid collisions with the workspace. It's kind of a basic capacity that we want our robots to have. But when we want to have proactive behaviors, so behaviors where we might synchronize with another human, propose to hand over an object, or propose to carry objects for the human, we must coordinate with the humans and so have a model of what the human's movement might be, so understand the human movements and understand the human intent. So this is already moving away from the traditional pick and place pipelines in robotic manipulation and going towards giving and receiving co-manipulate objects, such as here, what we see here, where there's coordination between the agents and there's also obstacle avoidance in this constraint environment here. Okay, so what this talk is about dynamic social movement. So it's movement that considers other agent in constrained workspaces, so such as a cafe here. One of the key aspects of these movements is to be able to anticipate what the other does. So with just a partial perception of what the other agent movement is, we should understand what is the intent and anticipate the other movement. Another thing is we should be able to, through our movement, express our own intent, which is kind of the counterpart of anticipation. Then coordination is really reasoning on that anticipation that we have of the other and producing a movement that, our own movement that considers the movement of the other agent throughout time. And finally, we want to be able to learn from other agents, that is to demonstrate, for example, a task to another agent, or learn by observing another agent. And all of these capabilities rely on having predictive models, understanding the human movements for robots. So traditionally, so this is I extracted this from the Handbook of Robotics. And this is version 2016 of the handbook, where the key challenges in human robot interactions are listed so. So there's the robot models, where the idea is that for robots, it's important to understand humans. For humans, we need to understand what kind of models they have of the robots. And then we need to have models of how humans and robots interact. So in this talk, I'm mostly going to talk about robot models, and towards the end, I'm also going to propose a way that we can demonstrate tasks to robots in a teleoperation fashion, where we really consider what is the underlying optimal policy that the robot has. Okay, so moving away from the traditional pipeline, we want to introduce a human estimation, so perceive the human directly, have a complete kinematic understanding of what the human is. This is going to, of what the human configuration is. So this is our age, and we are going to blend that into so this is our perception pipeline. Then we're going to use these estimations to produce a prediction and then perform optimal control, which is going to, I will show how we can do coordination using these predictive models. Okay, so my talk is going to be like this. I'm first going to give a quick overview of human-aware motion planning. I'm then going to talk about inverse optimal control and collaborative motion. So that's the idea of learning from demonstrations of human movement, what are their preferences in order to predict movement in an optimization framework, or to produce collaborative movement. I'm going to show how we can then move away from linear inverse optimal control into combining constraints with data-driven dynamical models, so low-level dynamical models that encode the human movement. And then finally, I will talk about how we can teleoperate robot, or actually demonstrate tasks to robot considering the underlying optimal policy, which leads to the natural gradient shared control framework that we presented at Roman this year. Okay. So, when we talk about human-aware motion planning, we are really reasoning on a collection of spaces. So the idea of human-aware is the idea of introducing the notion of proxemics. So it's this notion that all humans have in terms of how they should be sharing the workspace with other humans. So we can divide elementary cost terms that are defined over the workspace, and then we can map these cost terms, so what states in the workspace are acceptable in terms of movement. So for example, visibility is very important, either to limit the effect of surprise or to limit the interference that we might have if a human is watching something, talking to somebody. And we can map these costs into the configuration space. Once we have them into the configuration space, we can reason about planning in trajectory space. And we can use either global trajectory or motion planning algorithms such as RT star, or here it's the transition-based RT. And we can also reason locally in trajectory space, which is what I propose in the introduction, where we perform trajectory optimization. So here it's a stochastic algorithm that's going to sample nearby trajectory in trajectory space and combine their cost in order to produce an update. The idea of extending these algorithms to human-aware algorithms is to move away from simply finding a path, which results often in high proximity with the environment, to reasoning about cost landscapes. And here we have defined a cost landscape around the human, and we use a combination of transition-based RTs and stochastic trajectory optimizer for motion planning to produce the movement. Another thing that we introduced is reasoning in the combined configuration space of the human and the robot to produce proactive handover movement. So here we have a very basic understanding of human movement, which is a purely kinematically feasible movement, and we just consider that the human move in shortest paths, which is true in most cases and is actually a good model for a lot of applications. Another thing that we introduced was how to reason about human movement when planning for robots by introducing workspace occupancy predictions. So here this was featured at IROS in 2013, so already a while back. But the idea was that we would combine over different classes of movement that we would observe their voxel occupancy, so their swept volume, and we would combine them for the number of classes and have a probability of being occupied for a given voxel condition on the trajectory that we observe. So this is what we see here, where initially we have an initial guess that the human is moving towards an object placed on the right side of the table, and as we observe more trajectory, we are able to correct our prediction, and in the middle we actually blend the swept volume predictions here. And then the algorithm that we proposed was to use trajectory optimization to minimize the penetration in this volume. So this is good for limiting interference and provides a general framework for human-aware motion planning, but it doesn't give a concrete data-driven way, or even, so we have some ideas about what the features might be in the workspace, but we don't have a way to combine properly these different features in order to produce these kind of proxemics theory. So in the second part, what I addressed was to propose inverse optimal control as a way to combine the different cost terms composing the human-aware cost function that the motion planning algorithm were reasoning on. So the idea is to first have a set of demonstration of how humans might share space, what is a good proxemics behavior, so we observe. And then we propose a bunch of features that might explain this behavior. We are still in this context of a state estimation optimal control pipeline. And we perform inverse optimal control in order to find a good weighing of the different features that explains the behavior that we observe in the demonstration set the best. So for example, here if we have a navigation task in 2 dimensions, we observe this S movement. The algorithm proceeds this way. So this is a sampling-based algorithm where we sample trajectories, and then the cost function that we would obtain is simply a weighted sum of radial basis functions. So this is just a toy example to explain how the algorithm or how to give an intuition about inverse optimal control in motion planning context. So in the human-aware motion planners, we do not use radial basis function, but rather more complicated features as I just presented. So here the features are simply a distance between waypoints of the paths and particular points in the environment, which are spaced on the grid. And what we can see is that the result of the inverse optimal control algorithm is going to give high cost region here and here, producing a valley where the lowest cost path is going to be this S path here. Okay? So this is our trajectory, and our cost function is defined as an integral over the weighted sum of the radial basis functions. Okay, so this work was started initially by collecting a data set where we have motion capture of 2 humans, and we see that there are movements where there's interference between the 2 humans, and we want to see how humans share space and what is the kind of underlying theory of how they share space. So first we have a learning phase, which just described on this toy example. So we sample trajectory using a Gaussian which has a particular form, which is saying that the trajectories that we sample should be smooth. Then we evaluate the features for all the trajectories, and then we solve a convex problem that has to do that has like a softmax form in order to which is mostly about the regularization term, which is the partition function. So it defines a probability density over trajectories, and we want that our demonstration is the highest likely trajectory of the whole set. The prediction algorithm is then going to be a stochastic trajectory optimizer, so that optimizes over the cost landscape. So what we introduced in 2016 was the notion of Goalset trajectory sampling, where we would modify this the way that we would sample the trajectories, and then project the sample to a goal region with respect to the same smoothness metric here. So that's the form of the convex optimization problem that we obtain. So this is kind of summarizing the method. We first collect data on this experiment. This data is being segmented by trajectories. We sample trajectories around each of the trajectory that has been collected. This generates a huge data set of features, so we evaluate the features for all the trajectories, generates a huge data set. And then we solve this convex optimization problem, which has to do with probability distribution, where we want to maximize the likelihood of the demonstration divided by the probability of all the trajectories to be there. So we want to find a weight vector, an optimal weight vector, that maximizes the likelihood of our demonstration. So we initially used these features that we see here. So we have smoothness features that have to do with the length and some of acceleration, some of velocities. We have interpersonal distances, which are depicted here. So it's an interaction mesh between the different body parts, and we compute what is the distance between all these body parts. And we have configuration kind of rest posture, and so this is for solving for the redundancy that we have of going to a certain point, reaching for a certain point. We have an infinite collection of configurations which are likely for this point, and so we need to have some rest configuration posture. So some configuration metric here, configuration space metric. Sorry. So what we found was that, of course, the wrist-to-wrist distances are actually not important, and things that are important are really wrist to pelvis and other body parts which are listed here. We can also see that the velocity is actually, the joint velocity is actually not important at all, but rather the joint accelerations are more important, and same for the task space. Jerks are also important there. So then we conducted a human-robot experiment to see if the predicted model that we learned from human interaction would map to human-robot interaction. It would predict how humans would move with a robot. And what we could see is that as a user would perform more and more runs with the robot to do this manipulation task, our model would actually, the prediction capabilities of our model would increase over time. So we would not only outperform baseline cost functions, but we would also outperform the cost function over time. So the initial predictions that we would get would not map, but as well in the beginning as at the end. And that's the idea, that the humans adapt to the robot and behave more and more like they would with a human. So we used, we collected 15 users and had 8 execution per human. So this is what we see, like these 8 different set of experiments. And this resulted in about 2,000 trajectories, which were segmented. And we could see that we outperform Gaussian mixture model prediction, and there was this behavior that I just described. So for the metrics, we use joint center, which is kind of classic in human movement prediction, and as well as task space metrics. So where we combine the rotation at the wrist with this formula here. This is the quaternion. Okay, so this linear way of combining the different features is clearly limited. We can only capture whatever we have, we propose in the feature set. And so as we wanted to move towards full body human movement, we started to investigate encoding in the short-term model the dynamics, some kind of dynamics of the human. So that's what I'm going to talk about now. So if we look at long-term activity and motion prediction, the pipeline is similar to what we would have for a robot. So we have at a low rate, we would predict what is the activity, what is the human doing now, maybe cleaning the table, maybe the human is resting, or whatever. If we look at manipulation tasks, we might have, that might be a reaching, a placing, a pouring, a drinking action, and so on. So this is at a kind of slower rate. Then we have motion prediction, which is about this kind of 10 hertz REM, where we want to, over the course of 1 second, we want to have a motion trajectory or collection trajectories, distribution over what the human, how the human is moving. And then if we look at a very, very short-term prediction, we might be interested in predicting forces. What are the interaction forces between the human and the table, the human and the ground, and so on. So there we also collected a data set So this dataset has been submitted and is under review. But it's already on internet, and so the link is right here. So you can have access to this dataset. So what is this dataset? So it's a collection of pick and place movement for tasks such as setting the table. So there are actually 7 different activities. Putting back everything on the shelves and walking around in an environment where there are chairs and there's some kind of motion planning behavior happening from the human. So the originality of this data set is that we combine full body motion that we get through this OptiTrack tracking system with gaze, where here we use a pupil sensor. So the camera is looking at the pupils of the user, and these are being aggregated. So the gaze data is aggregated with motion data in order to produce this full body movement with gaze tracking. So we do this because we believe, so there's a lot of evidence for that gaze is actually a very good predictor of the activity. So especially when we want to perform a pick action, we really look for the object that we want to pick, and then this is going to predict what is the kind of goal configuration that the human is aiming for. And given that, we can have better movement prediction. So we have about 2 hours of data at 120 Hertz, and this results in about 1,600 pick and place actions that have been segmented. So we then looked into predicting sequences of movement, so about 1 second trajectories, based on observation of past observation of movement. So here we have the beginning trajectory in blue, the end trajectory in green. And the idea is that capturing the biokinetic mechanical dynamics is actually really hard. Linear models for this are really limited, and it's difficult to design good features in general. That is because there's so much synergies in the human body. There are so many muscles and tendons and so on being considered that the models that do that right do not do that at a rate where we can use them on the robot. So that was kind of our starting point. And the solution is the idea here is to separate the control and the environment constraints. So the environment might be it might be the different chairs, how the different chairs are placed and so on, the geometry of the environment. And the control is going to be kind of like the smoothness and what I just described about the human body. And use a deep autoregressive model, so basically a recurrent neural network in our work, to model this kind of short-term dynamics and then optimize these short-term dynamics given the constraints. So what is a recurrent neural network? So it's basically taking initial states that we observe. It processes them through a hidden layer that has access to the previous hidden layer state, and then produces a prediction for future time step. So if we unroll a recurrent neural network, we'll see that the hidden state is being translated over time up until the time where we produce the prediction here. So to train this recurrent neural network, there's backpropagation through time, and this has been implemented on most of the deep learning frameworks, or all the deep learning frameworks. One of the very popular ones is the LSTM, but we don't use that in our work. Instead, we use GRUs. So how can we combine this data-driven dynamical model with trajectory optimization? So here the idea is that we perform maximum likelihood subject to environmental constraint. So this is like a very high-level mathematical description of what's happening. So we minimize the log likelihood of the recurrent neural network or our autoregressive model. So this is a regression of a model. We model our data set here that we acquire through motion capture and gaze observation. But then we produce the prediction subject to constraints that have to do with the environment at each state. And this leads to a augmented Lagrangian trajectory optimization algorithm where we have a control cost that has to do with minimizing the deviation from the RNN with an environment cost which takes into account the RNN prediction, which is based on the deviation itself at every time step. So here we have feature K, which are the elementary constraints that we might consider. And this has the classical motion optimization form of having a control cost and having an environmental cost, which is linked to the state. So when we optimize that, we have to derive a gradient for that. And that means that we have to actually use the Jacobian of the recurrent neural network. And so what we're working on now is to have a formulation of that optimization algorithm, which doesn't require the computation of the Jacobian, which is the highest computation cost in this framework, but rather have it done internally by the deep learning framework. Okay, so how does that work at prediction time? We have observations in blue here, so these are the joint velocities and states in blue that we have observed so far. And then the unrolled RNN stops here, and then we chain prediction over time. And so what we introduce here is this deviation parameter, which if you look at the architecture is equivalent to an acceleration term. So what we are penalizing in the motion optimization for motion prediction framework is to penalize the extra acceleration that's being done on top of the data model that we have. So acceleration kind of mapped to internal torques. So this is kind of the intuition that's happening here. So we have here our observed states, we have our predicted states, which are those here, our velocities and our deviation from the prediction. Okay, so if we look at results here, so we have the ground truth on the left side and the prediction on the right side, and we use two environmental features here. We use the hand goal position at the final time step, and we use the sign distance to obstacle for the pelvis. So what we can see is that the ground truth and the predictions are very close, and we also confirm that statistically that by considering both of the constraints, we outperform just considering the goal constraint, and then we outperform by a very large margin, just not using any constraints here, but rather only using the control cost, which is being driven to zero. So that's like the unroll of the recurrent neural network. So then the challenge is really, how do we come up with these constraints online? So what we propose here is to extract features from the environment and learn some kind of affordance model. So in the general theory of affordance, we really have an agent and an environment and a given action. So that here might be a grasp action or a place action. And these together are combined into an affordance model. So in the model that we propose, the affordance densities are actually Gaussian mixture densities. So this is what we can see on the table here. And we process the table plane features. So here it's an occupancy grid from a top-down view of the table. So it's taking away like the different objects that are on the table. And then the agent is also modeled with a recurrent neural network, which is here an LSTM. So that's like, we model the state, we encode the state of the agent as like the kinematic state of the agent. And convolutional neural network is encoding the features of the different planes for pick and place actions in the environment. And the affordance density is going to lead to different densities for where to place the different objects that we have observed from data. So if we use the hand goal as the maximum likelihood point on these densities, we have something that we observe here. So this, here we have just extracted these constraints from the data, not like the oracle way that I just showed before. And so we can see that the prediction is also very close to the ground truth in gray. Okay, so this is just the final, can put everything together. Note that this work has been awarded finalists at best paper finalists at the last ICRA. So there we do human-robot coordination. So the idea is that we have a negative log likelihood term on our data set, which is our human motion prediction here, and we have a robot cost term, which we have designed ourselves. And the constraints are not only about the human state anymore, but they combine the human and the robot state. So we basically mix prediction and planning, and we mix the learned model with the robot, the engineered model. And what we can see is that when we have no objective, common objective behavior, the prediction kind of runs through the robot, and in the other way, the robot actually deviates from its path. In order to let the human, and that the human also deviates from the prediction, but in a minimal way. So it's really a coordinated plan that we have here. Okay, so that was it for motion planning with human movements and human-aware motion planning. And now I'm going to talk about how we can demonstrate or how we can teleoperate robots with movement. So consider the problem like the classic teleoperation setting. Here with a Baxter, we want to pick up an object, and we have Baxter observes the scene through some sensor. But we want to teleoperate the robot with some movement and maybe additionally some gaze tracking. So in these cases, we might have a complete optimal policy for the robot, which is the case we consider. And we need to somehow map the intention or map what the user demonstrates to the robot in a way that it matches the optimal behavior encoded in the robot policy. So here human movement understanding is very important, because in shared control we usually want to extract the goal and kind of use the robot policy in order to perform a certain goal. And note that the prediction models that we have here are also based on recurrent neural network, and they are affordance-like prediction models as well. So what we introduced at the last Roman conference is the notion of natural gradient shared control, where if we formalize this idea that we want to execute an action that is as close as possible to what the robot policy has, so our shared policy here is maximizing whatever is the internal cue, so internal action value function that the human has, but subject to not being too far away probabilistically to the robot policy here. And we assume that we have this robot policy. So we really derive this framework in the context of movement, where the actions are really tangent vectors to the state manifold. The simplification we make is that we assume that we have one, so that we don't have access to the action human value function, but rather we have access to samples of it, which are gradients according to the state of this. So these are like a single action here. And by looking at a differential version of the Kullback-Leibler divergence here, this produces the robot Fisher matrix that we have here. in order to project control input from the human on the optimal robot motion policy space. Okay, so in our experiments, we consider a pick and place task where we have on a plane, so we have a gripper and we go towards a goal, and then we retrieve to a place position. So these goals and these place positions are parameters of the optimal policy. Our optimal policy is derived from performing a lot of optimization queries and regressing them into a neural network. And we also correct here for having like a minimal minimalistic avoidance field around the obstacle here. And what we see in the center, so each of these ellipsoids are really the Fisher matrix at this particular point for the policy, and and what we see here is a belief weighted over goals. So we have different goals that parameterize 3 different policies, and then we blend the different ellipsoids here. So the Fisher information matrix is calculated here by differentiating the policy, and so this is explained in the paper. I won't explain how we do that, but it's basically using linear weighted regression and sampling of the policy. Okay, so the results that we got here with 3 different goals that change, and over an experiment, I think with n is equal to 16, but I'm not 100% sure. This has to be in the paper. This has to be checked in the paper. Okay, what we saw in this experiment is that our method here, which is always the second one, compared to 3 other baseline, is the one that takes the less time for the operators, minimizes the travel distance for the robot. So that is not true. That doesn't minimize the travel distance, but is very close to minimizing the travel distance compared to linear blending here. But what happens is that we are further away from obstacles, and what is much more important in the comparison to linear blending is that we give control authority to the user by having lower cosine distance. So the first one here is direct control. So direct control is the one where we perform no blending between, so there's no consideration of when the optimal policy of the robot might be. Then we have the linear blending. So here we also consider the optimal policy of the robot, but rather we simply blend the actions that would. So we use a predictive model of what the human goal might be, and then we use this predictive model, the confidence on this predictive model, to blend the actions between what the human wants and what the robot wants. And so there we lose a lot of control authority, so the robot takes over much more often. And what we can see is that this is also less efficient in terms of time, so the natural gradient shared control is also faster at performing these tasks. Okay, and finally we have just a baseline doing only obstacle avoidance. So here also the control authority is very high. So the cosine distance is very low. And we also avoid completely any proximity with the obstacle. But in terms of time, this is the less efficient one. So yeah, so here we can get kind of stuck in minimas and so on. So the takeaway is that with this natural gradient descent, where the action is on the tangent space of the state space, we basically have maximum control authority while keeping all the benefits from considering the shared, the robot optimal policy. Okay, so in conclusion, I presented things about robot and human model. So here we have kind of like the basic notion of avoiding behavior which doesn't really consider humans, and I presented how we can really have a refined human model based on data-driven models that we can use for coordination. And finally, I presented this interaction model, which is really here. It's a model interaction that has to do with really considering the optimal policy when we want to control our robot on the tangent space of the state space, or the configuration space. So human awareness really requires predictive models. I hope this is clear throughout the talk. For safety and comfort, which means like being socially aware, we need to have predictive models of how humans move. Then the question is, what kind of model do we need? And often, as I said in the beginning, humans move in the shortest path. So depending on the application that we want, we don't need very complicated models. But when we start to have richer perception of the human, so we can track the gaze and we can have like a full, we maybe have close interaction with the human, where we have a full kinematic tracking of the human, then we want to have full body motion predictions, which really make sense in terms of dynamics, or in terms of like the kinematics of how the human movement unrolls. And there, I believe that data-driven models allow for really sharp predictions, which are also kind of time efficient. And they can be used in optimal control framework. This is what we proposed at ICRA. And but there's really a need for alternative interaction models, where we really in the future are going to have optimal motion policies for our robots, which are going to be derived from a lot of offline reinforcement learning, and we should be able to make use of these optimal policies when we demonstrate, when we teleoperate, when we collaborate with robots. So the challenges are already in this line of work: understanding human movement, like what are good models of affordance, how we derive them from data, model, robots being able to really know what humans think, kind of, and that's like the theory of minds. And the theory of mind. What is the human model of the environment right now, so that I can help the human the best productive way. Finally, what I think is really exciting is this notion of hierarchical representation for behavior models. So not only short-term dynamics, but also reasoning on what is in the environment, having models that produce densities over the environment and so on. I want to thank all the collaborators, especially Marc Toussaint in the recent years, and my PhD students that are here. And that's it. I hope there's a question session. Otherwise, you can always email me or get in contact with me. Thank you.